Hi everyone, so my name is Chen-Yu. So I'm happy to be here to share our paper, which is called the Oasis, an overcore approximate graph system via the all-distance sketch. So this is a joint work by the Chen University of Hong Kong and the University of Texas and Dallas. So this is today's outline. So we will begin with the introduction. So to begin with, that the graphs are an incredibly powerful data structure that can express a wide range of the real-world relationships. And they do this by storing the entity as vertices and the connection between entities as edges. But what really sets the graph apart from the other data structure is the concept of the neighborhood. So in other words, is that how a vertex is connected to the other vertex in the graph and can actually provide some crucial information. So many important applications that rely on the neighborhood information. For example, like the social network analysis, we will often need to understand the user relationship to identify the influencers. In the recommendation system, we will also like to find some similar user or items that with some shared connections. And in the navigation planning, we also need to determine we often need to determine the shortest path from the location A, for example, like for location A to location B. So to tackle this graph application, that one direct approach is to use the in-memory graph processing. So where we will store the entire graph inside the memory and try to process the graph. So this method is efficient, but it can be expensive, especially for a large-scale graph. And another approach is the out-of-core graph processing, which will keep the graph data in the storage, and we only load a small part of them into the memory when needed. So this is more cost-effective, but it often limited by the slow I/O bandwidth. So due to the trade-off between the in-memory and out-of-core graph processing, so we start to looking at another direction called the approximate graph processing. So the key insight behind this exploration is that in many real-world applications, that the exact answers are not always necessary. So this actually offers us a room to leverage the approximate method to break this the trade-off that we are talking about in the previous slide. And among those approximate approach, we found that the all-distance sketch, or we just simply call it as the ADS. So the ADS has recently emerged as a promising scheme that can capture the neighborhood information. And to be more specific, the ADS is a probabilistic data structure that defines for each vertex. And it's a sketch that to summarize how a vertex U is connected to other vertex in the graph. And to be more precisely, an ADS of a vertex U, they will contain the distance of the U connected to other landmark vertices. So according to an existing study, the ADS is the only sketching scheme that combines the following three characteristics. So the first one is the multifunctionality, which means that it can be deployed for various applications. And the second one is the controllable and guaranteed accuracy. It means that the user can adjust the parameters of the ADS to control the error bound when they try to do the estimation. And the final one is the scalability, which means that the space and the time complexity for using ADS will grow nearly with the graph scale. So however, despite the fact that the ADS is well developed in the theory, there is still a wide gap from its practical use in the real world cases because most of it because of it requires excessively high memory consumptions. So here we list some key challenges. So first is that the recent effort in the ADS, they will mainly focus on the theory perspective, and they propose algorithm with all in-memory environments. However, the state-of-the-art scheme, based on our study, the state-of-the-art scheme that can efficiently construct the ADS of all vertices, they will require an enormous amount of memory. And this amount of memory can be up to like 50 times larger than the graph itself. So yeah, they will actually have a very high memory overhead. And the second is that since the managing the ADS is more complex, so most of the technique from the existing out-of-core graph system is actually ineffective for the ADS scenario. So if we just simply running the ADS construction on the traditional out-of-core graph system, they will often lead to a very poor performance. So due to this challenge, we proposed the Oasis, an core approximate graph system that try to bring the ADS technique into practical use by leveraging the storage effectively. So for the next part of the slide, we will talk about the background of the ADS. So this slide, we briefly go through the theory of the ADS. So given a graph G, the ADS are defined with an integer parameter k and a random assigned function r to all vertices. So the k is the parameter that can decide the trade-off between the sketch size and the estimation accuracy. So if we set the k to be a larger number, then the sketch size will also become larger, but and the estimation accuracy can also be higher. While r is a rank function that will where the r over v will be mapped to a value between 0 to 1 for any vertex that belong to the graph. And the following three formula, they will show the details about how the ADS will select the landmark vertices. But we're not going into too many details in here. So what important is the form of the ADS. So it can be shown in the last formula here. So in the last formula, each ADS is we can see that each ADS is actually an array. And each element in the array, they will contain a vertex v, which is the landmark vertex, and also the distance from u to the v, the landmark vertex. So the size of ADS is about big O of k log v. So the total size of the ADS is v times k log v. So it can so this size can be much larger than the graph itself if we set the k to be a larger number. And for the real-world application, that the k is usually tens or even like a few hundred. So yeah, so this slide shows the workflow of using the ADS. The ADS, it will involve two main steps, which are the ADS construction and the ADS estimation. So the first step, so when we have a row graph, we will first go into the first step, that is the ADS construction. It will try to produce the ADS based on the row graph and also depend on the k value. And after we have the produced ADS, the ADS estimation will use the produced ADS to estimate the approximate answers. So since the ADS is only a data structure, so there are many existing efforts that try to propose some methods they will study how we can actually calculate the approximation answer by using the element of the ADS. So for this method, we will often refer to them as the ADS estimators. So in general, the ADS construction, they only need to be performed once per graph. And we can estimate various graph properties and application multiple times through those ADS. So this capability are crucial for the application that require a substantial computational workload, or those that need the quick interactive responses, such as the drill down analytics. So for the next part, we'll introduce our system, the Oasis. And so this figure shows the system architecture and the workflow of the Oasis. So it mainly consists of two main modules, the ADS construction module and the estimation module. So the user will provide the two inputs, the k value and the available amount of memory that can be used by the Oasis. So these two will goes into the ADS construction module. So the next, the Oasis will process the row graph and generate the ADS while storing them inside the storage. So once the ADS are ready, the user will supply their ADS estimator to our estimation module. And finally, this module will take over. The estimation module will take over and try to optimize the process of loading the necessary ADS and running the estimator to generate the approximate answer. So for the Oasis ADS construction, the first and the most important challenge that we face right now is to reduce the memory consumption. So to tackle this, we will use a partitioning-based approach to help to manage the limited memory while ensuring the good local access. So partitioning is a well-established technique in the traditional core graph systems. So the key idea is we can divide the data into multiple disjoint partitions. So this allows us to process only one or two. We can only process one or two partitions at a time, so which can effectively keep our memory usage low. So given that the ADS are large, so the partitioning is actually a natural fit for the Oasis. And because we also use the partitioning, so this means that the user can adjust the number of partitions based on their machine's memory capacity, making it possible to run the graph of different scale with the Oasis. But to make the thing more efficient, we further break an edge grid into multiple equal-sized blocks. And each block will holding a disjoint set of the destination vertexes. So by doing this way, the different thread can process a different block. And because they were holding a disjoint set of the destination vertexes, so which means that we can prevent them from updating the sender ADS at the same time. As a result, that there will be no need for lock to handle the conflicts. We can keep the process smooth and efficient by using this block design. So since the ADS is the largest data structure during the construction, so how we can minimize IO amount of load in the ADS is crucial. And active data separation, and we propose the active data separation as a technique that we can try to minimize the loading for the active ADS. So the active ADS, it means that the set of the ADS that require processing in the current iterations. So the left figure, we show a very simple example. We have the update X that will push from the vertex A to the vertex B, and where it gets added to the ADS of B. So in the next iteration, we will also, the update X will continue to move forward. They will getting pushed from the vertex B to the vertex C. But with the traditional method, we have to load the entire ADS and search for the active ADS. But this can be very inefficient because we only have a small portion that's needed. So the active data separation is proposed to tackle this issue. We duplicate the active ADS and store them in a separated file which contain the active ADS only. So in the next iteration, we don't need to directly read the data from the original ADS file, but we can just directly read the separated file that hold the active ADS only. So we can use this one to save the I/O. So the process active ADS can be deleted in bulk in the file because the construction, they will produce a new active in the next iterations. So the next we have, for the next technique, we have the selective ADS accessing. So this technique is further to design to reduce the unnecessary ADS read by loading only the ADS that actually received update. So we also look at this simple example. So suppose that the only new update in the entire graph is X in the vertex B. So instead of blindly loading all the ADS, this approach will first spend some extra I/O read on the edge data to get the neighbor information. So by doing this one, we can identify which vertex are truly needed and load only those ADS. So in the example, we can see that we only need to load the ADS C and ADS D. So it's important to know that because the edge data is usually much smaller than the ADS, so spending some extra read for the edge data is actually worth it because compared to the I/O saving from reducing the ADS read. So in this slide, we will discuss. Okay, so these are all the design that try to optimize these ADS construction. So this slide, we show the framework of our Oasis ADS estimations. So we will discuss the Oasis ADS estimation. It will contain it mainly contains two components. The first one is the ADS estimator. They are provided by the users, and also they have a query queue. The query queue is also filled by the author to indicate which ADS is going to be loaded into the memory. So each query in the queue contains information of the target vertex ID, which means that the ID that the ADS needs to be loaded and estimated, and also the pointer. So they will point to the correct ADS estimator. So if the user can fill up the ADS estimator and the query queue, then our Oasis will automatically process this query and try to optimize the performance when we try to do the estimation. And the main observation in this framework is how we can assign the queues to the different thread. And this kind of attack assignment will largely affect the overall performance. For example, like if we have a thread that we assign with a memory query requiring the same ADS, then the thread will only need to load the ADS once, and it can serve many queries. So this will can significantly improve the IO utilizations. So for this purpose, we have proposed 2 different methods that try to improve IO utilizations. But due to the time limit, I will not go into much detail for this one. So if you are interested, please refer to the papers. So for the final part, we will talk about evaluation. So we compare our Oasis against the 2 in-memory schemes. We call it the basic and the SOTA. So the basic is a straightforward implementation of the ADS formula directly. It will perform the graph traversal from the AV vertex, and the number of edge traversal is high. It will actually require bigger of V times E. And the SOTA, on the other hand, is proposed to achieve significantly lower time complexity. It has a special, it is pretty special because it tries to run on the transpose graph. So the SOTA can perform the bounded graph traversal. So different from the original graph traversal that need to traverse the entire graph, the bounded graph traversal, they can be trained the traversal when needed. So the number of edge traversal is only bigger of EK log V, which is much less than the basic scheme. So our Oasis ADS construction is to try to combine the SOTA scheme with the partition technology to reduce our memory consumption. And we also propose other optimization that try to improve the overall ADS construction efficiency. And for the following experiment I present, we will use the 16, we divide the graph into 16 partitions by default. But of course, if we try to divide the graph into more partitions, then we can have a lower memory consumption, but longer execution time. So due to the time limit, I will try to quickly go through this evaluation result. So basically, our Oasis scheme is actually, so the first row shows the execution time, and the second row shows the memory consumption. So we can see that, and the purple one is our Oasis scheme. So we can see that our Oasis scheme is actually still worse than the SOTA scheme because they are the all in memory. They will assume they will process all in memory. It will about 2 times longer. But when we come to the memory consumption, which is the second row, we can see that our Oasis can require about 10 times less memory overhead. So we believe this is a worth deal because the considerable amount of memory saving, they will enable the ADS technique with the reasonable cost. So this slide we shows the design choice of the ADS, the design choice of this Oasis ADS construction. So the most effective one is the active data separation, and then the edge block, and then the selective ADS accessing. So this slide we shows the conclusion, which is where we introduce a system called Oasis. And we try to manage the ADS with the low memory overhead and high efficiency. And that's all for my presentation today, and thank you for your attention.